here I have 4 optimization parts, and later I will bring them to the VITIS system, and there are some to-dos. Okay, so the first, we can see that Kolitsky is a metric decomposition problem. It actually decomposes a metric into a lower triangle matrix, and we can see that for each column data, the order of the calculation cannot be changed. That is to say, if we want to compute the second column here, then we must compute the first column first. So and here are some insights for each column data. They can be computed in parallel. However, the order cannot be changed. And here is the equation for reference. And for Kolitsky decomposition, the metric A itself should be symmetric and positive SPD metric. Okay. So the first part, the no pragma version, actually in VITIS HLS, it is a default pipeline version. And the code here mainly contains 3 parts. The first part is read the whole data here. And the metric here I use is 512 by 512. So we can see that reading the data with I equals to 1 results in the square of 512 cycles. And it is similar for the write data part. And in this case, the main kernel here, in the code here, we can see that we have a first loop column here. And it actually computes the lower triangle metric, the first column of the lower triangle metric. And then the second part is for each column here, each other column here, we are going to calculate first the diagonal term here. So we have a loop diagonal here. And then later, we'll compute each row below this column, below the diagonal term here. So we can see that after calculating the first column, then we have a loop called loop column. And in this big loop, we have 2 smaller loops in parallel. So we first compute the loop diagonal term, and then we compute the rows below this diagonal term. Okay, and we can see that there is a problem when pipelining the loop diagonal, the for loop here. And we can see that the II equals to 6 when pipelining. And we can see that later why this will happen. And the iteration latency here is 16 cycles. It consists of 2 read and 7 multiplication and 7 add, because the data type here we use is double. So the multiplication and addition hardware takes much longer cycles. Okay, and actually what the loop diagonal really does is inner product. We can see that it takes the column J. For example, we take the second column here, and then it simply performs the inner product between column J, 2 column J's, and it only multiply the J-1 elements in column J. So it is simply an inner product here. And actually, after calculating the diagonal term here, we are able to calculate the other rows below this diagonal term. And we can see that loop row here also it consists of 2 loops, and the innermost loop is another inner product term. And later we'll see that actually the innermost loop here also has the I equals to 6 problem. And both of these two, the problem here is because then we have a plus equal data dependency here. Okay, so we can see that from the schedule viewer here, there are 7 multiplication, 7 addition here, and 3 reads for the inner product, the second loop here. And we can see that the reason why the I equals to 6 is we can see when we want to make this addition here, and we simply can't do it if we use I equals to 1. We can see that if we want to make this add here, okay, if we want to make this add here, we can find out that the previous adder output is not yet ready, and because we all want to sum into the single variable temp2 here, so I equals to 6 here. And if we want to resolve this, one possible method is to use we break the data dependency by adding another additional buffer. That is to say, we store the intermediate values into a buffer with a depth greater than at least the II value. So since we have I equals to 6 here, so the buffer depth here should be greater than 6. And later, after we store these values into the array, into this buffer, we can later sum the buffer values up, and we use an adder tree to sum the final result. So we can see that here the array length is 16, and there is no problem here because if we want to perform I equals to 1, then after we can see that after 16 cycles, we will overwrite the previous element 0 in this temp buffer. But at that time, the value is already updated, so there is no problem here. And we can see that after performing this, the I equals to 1 in both the 2 inner product loops here. And the max cycle here decreases. Okay, and here the summary here, we can see that the iteration latency is actually it is actually not a constant. That is because Kolisky is a special algorithm. We see that we compute each metric columns. We compute the output column by column, and the computation, the elements we need to compute in each column is different. So actually, if we move on to the last column, we can find out that the computation increases. So the trip count here also varies. However, we can still compare with the max cycles. For I equals to 6 here, it is approximately 1.5 million cycles here. And then after I equals to 1, we can see that it is 0.26 million cycles. And the hardware utilization, actually it doesn't increase very much. And later I perform unrolling because we said that Cholesky factorization can be performed in parallel within one column. So for example, if we want to compute column 2 here, we can compute the different rows in parallel. So we can split the metric into tiles and perform the pipeline inner loop product in parallel. In this case, the NCU means the unroll factor, and in this 512 metric case here, I use 16. And there is some problem when doing the unroll. It's not just simply applying the pragma unroll here. That is because, again, Cholesky is a special algorithm. Although we say that the rows can be computed in parallel, however, they will use the same data. One of their computing elements they will use the same metric tile here. So we can see that the code we refactor here, also it consists of 3 parts: the reading part, writing part, and the kernel part. However, there later we'll see that we will have one additional static array here. Not this one, but another one. And in the previous case and in this case, we will also need the whole 512 times 512 metric to be stored in on-chip memory, because later we'll see that I think we cannot avoid it. Okay, and here we can see that we partition the array into the first dimension is the 16 loop unroll factor, and the other one is if this is 16 and the second dimension will be 32, so 16 times 32 is 512, and max is 512 here. And we perform the array partition to the dimension 1 here, because we are going to access this static array in parallel in the first dimension here. Okay, and the cycles for read data and write data is similar, and the core here is refactor, and we can see that later. Okay, so after unrolling, we can see that the Cholesky core actually it contains a single big non-pipeline loop. It is called loop column, and in this loop, what it really does is performing the computation column by column. So here we have a column index j. It increases from 0 to 511, and for each loop body, there are 2 parts. The first part is for computing the diagonal term. It is called Cholesky JJ, and it must be computed first, because if we want to compute the row values below this diagonal term, they all uses the first diagonal term. So after computing the Cholesky JJ here, we can then compute the Cholesky column wrapper. It is actually a wrapper for the below rows. Okay. So for the diagonal term in each column, here we can see that the code body in a easier way to interpret this is given a column J, for instance, given column J equals to 3, we compute the pipeline inner product loops with its J minus 1 elements. For example, if we want to compute this metric value, the right bottommost value here, it is column J equals to 3, and we have to compute the list 4 values, and we have compute this vector, the inner product of this vector between itself, and it is the code is linked to this part. Okay, and actually it is just a loop, a vector inner product. So we can see that again we use the adder tree and additional buffer to reduce the II. And what we really unroll is the column wrapper down here. We can see that this wrapper, it consists of only one loop, and this loop is unrolled with a factor of 16, or we noted NCU here. That is to say, for each tile, for each metric tile, they can now be computed in parallel. So there are very many instances here instantiated. And also notice that there is a pragma data flow here, but I commented. Later, I'll explain why I commented it. And here, there is something special to mention. To perform unrolling, we said that we cannot simply add the pragma in the previous pipeline code. So in this optimization free part, I use another refactor code here, and we can see that here we have another buffer called data J. Actually, that is because if we want to compute the rows here in parallel, actually they will all use the same data. They will use the same data column, some column here. So actually there is 16 copy of this buffer here, and we can see that the data J array here is 16 by 512 buffer, and that is because we duplicate the same values and allocate them into the distributed parallel units here to avoid the data dependency problem. Okay. So actually, it is a little bit tedious because the code is very long, but we can see that what we actually did in this loop is that for each unit, it actually we have 16 units here in parallel, and for each unit here, given one column J, for instance, J equals to 2 here, and this unit will perform the rows. It will take one row here and then perform some computation. Actually, the computation is also some inner product. So we can see that again, there is a adder and the adder tree and the buffer here. So Okay, and these inner product loops are all pipeline and use the same techniques as mentioned before. We can see that the trip count for this inner product loop here is 1 to 511, because whenever the j increases, the loop bound itself will also increases. Okay, and before we perform the pipeline with I equals to 1 version, and we can see that the max latency here is we can see here it is the max latency here is 172 million cycles, and after unrolling, we can see that the max latency here, or we can see here, will become approximately 3 million cycles. That is 56 times better than the previous case, although we use only the unroll factor 16. And the reason is because after doing this unroll, we can further do some actually for each row here we can do pipeline, and there's more than a factor of 16 of timing improvement. However, the hardware utilization rate here actually exploded, especially the DSP part. Okay, and the fourth optimization here is data type. Actually, we want to ask what is the error tolerance for us before we use double, and for the algorithm part, maybe it is possible to use float. However, for a 512 by 512 metric, the right bottommost output value will have an accumulated error of maybe actually this is a little bit large. So it depends on how your algorithm can tolerance the error. Okay, and so in this slide, I want to show that we can use template functions for data types. For example, the loop here, or the function here, we use a template, and the data type here is we rewrite it as t, type name t, and it can be replaced with maybe float double or AP arbitrary precision integer, and it depends on what is your case, and it can be quickly modified without actually modifying all the data types. So we can see that if we add this to your function, then during initiation you just need to apply this this kind of thing, and you don't need to modify all the code. So we can see that after changing to float data type, actually the max latency decreased a little bit. However, the resource utilization decreases to maybe 0.5, and it is all depend on what is your error tolerance rate. And the last part is the data flow. Actually, we can, if we want to apply the data flow, we can just dive into your code and see if there is parallel loops, and maybe in the form of the canonical data flow form. And we can see that here for the inner product and adder tree, it looks like there is parallel loops here. However, actually they are not so useful. We can see that later. Another data flow we can apply might be the read, kernel, and write part. Actually, we can inline the Kolesky kernel core, and it is look like 3 loops in parallel. Okay, so for the first data flow optimization, actually it does not really help, because if we perform data flow, actually here we just sum up the values here, and it cannot be the output here will not be stabilized until the first loop is computed. So we have to wait for the previous output to get in order to get the final data. So actually, this is not feasible. And the data flow part for the read, kernel, write part, actually it is not trivial here, and maybe we can discuss later, because there is a feedback loop. We can see that for Kolesky algorithm, when we compute for example, the third column here, actually we have to reuse the data output from the first column. So after the kernel output from column to column, we have to output the data and feedback to the previous one. So the data flow here is not a simple consumer producer-consumer form. And I searched for the VTIS document. It said that if we change it to string data type, it can accept feedback data flow. However, it is also not so trivial, because the streaming data requires data to be in some sequential manner. However, because this Kolesky algorithm, the loop bounds varies from column by column, so the streaming data here will need to be more. We have to do more additional modification. Okay, and so actually I did not perform the data flow, and maybe we can see that actually the original code here, they add the pragma here, and this works. However, in my opinion, I don't think that it really does what we want, because actually here we have this loop and it is unrolled. So if we apply data flow, actually they are running, all the loops are already running in parallel, because we are unrolling the loop. So data flow here seems not to actually doing what we actually wanted to do. And I tested if we really add this back data flow pragma back, the latency actually increases. Okay, so we're back to the VTIS system part. So I put it on the U50 system and compare it with the CPU version. We can see that for 16 by 16 metric, actually the CPU runs really fast. And we can see that if we use pipeline I equals to 1, actually for 16 by 16 metric, the kernel still requires 0.21 milliseconds. And comparing to this, it really does not speed up. However, if we change it to a 512 times 512 metric, we can see that the pipeline I equals to 1 kernel. The kernel time still cost 10 times more than the CPU version. However, if we apply the on-road, we can see that the kernel time can slightly compete with the CPU version. And if we change the data type to float, it reduces to 10.7 milliseconds. I think this is reasonable because actually in modern CPU, the modern CPU is very strong and they have various compelling techniques. And if we simply use pipeline, and also the clock cycle in U50 cannot compete with the CPU, so we have to do on-roll. However, this implies that we have to use much more hardware resources. And actually 512, this metric is almost the upper bound of U50. I try to put a 800 by 800 metric, but it can't fill this FPGA. So there's one thing. We shouldn't put the whole metric into FPGA. And we can see that another thing is that for simple kernels, for instance, this 16 by 16 metric, the memory write and read actually takes approximately half of the kernel computation time. So the kernel here cannot be too simple. Otherwise, we cannot get any benefit. And there actually exist some other possible optimizations. For instance, we can store only the lower trigonal metric because Gleiski just only requires symmetric matrix as input. And maybe we can store the lower trigonal with less memory. For instance, use the use of sparsity. And also, I even try to think about if we don't want to put the whole metric into FPGA, maybe we can add line buffers here and apply the Dataflow like processing way. However, in Gleiski, actually I find out it is not possible because if we want to compute the last element output element here, actually we have to use the first column, the value in the first column. So if we actually just streaming in and streaming out the data with feedback, also with feedback here, we still cannot achieve this because the line buffer here, for instance, we already output the first column, the output of the first column. However, when we go over 512 trip counts, then we have to go back and get the first column output, which is already throwing out. So it seems that for Kolinsky algorithm, we must have a full metric, or maybe at most, at least a lower trigonometric here. Okay, so the summary here, we use the buffer and adder tree to resolve the plus equal data dependency, and we can use template to increase the code flexibility. And I also talk about some data flow issues about the feedback. I think feedback it can be resolved, but for Kolinsky, it seems not to be a simple problem. And another thing is that data transfer matters if the kernel cannot give a significant boost. Okay, so thanks for your listening.
Yeah. So this algorithm is not really fit into the for the parallelism. Yeah.
Yeah.
Mm-hmm.
And
so the I think the parallelism is mainly from the enroll.
Yeah.
Right. The
yeah.
You enroll 16 times. Yeah.
Yeah.
Okay. So for the enroll, since you enroll the function, so actually it duplicates the function 16 times.
Yes.
Yeah.
And the hardware resource, yeah, will explode.
Yeah. And for this, the 16 functions during the process, not all the computing element active at the time, right?
Oh yes,
And
it
the
is.
16 is a triangle, so actually the usage for the hardware decrease with the iteration.
Yeah, it is another problem. If we just allocate these fixed functions here, and there is a problem.
Right. Yeah. And those functions, since I mean the hardware resource is not fully utilized all the time during the process.
So I think that another way is to manually allocate the data into these PEs.
Yeah. So is it possible? It sounds like this algorithm can that be changed to systolic array. So that's a kind of a data flow, and systolic array probably can better use the hardware resource. Yeah, if you have a sequence of a matrix to compute, is it possible the next matrix can pipe in and use the resource?
Oh yeah.
I don't know whether people researching that area.
I think it is possible.
Yeah.
Here, yeah.
Yeah. So, for example, you have a sequence of the matrix you want to process. So you try to pipeline in next matrix and using those and use the computing resource.
Yeah.
Okay.
And another thing is that I'm not sure that if we can find this application. I mean, a sequence of metrics to be decomposed, because in most applications, the input metric itself is from another kernel, and the kernel will be it usually is very time consuming.
Yeah, and also involve the I/O. Yeah.
Yeah.
You only count the kernel time, and it's not much improved. And if you count into the I/O time, that will make it worse.
Yeah.
So I'm not sure whether this open source is the best or the most optimized solution?
I think maybe there is some other algorithm-specific solution to speed this up.
Yeah. Okay. Good.
Okay.
Yeah. Okay. Thanks. Yeah. It's good presentation.
I guess it's my turn, right?
Yeah. Right.
Okay.
Okay. It's Houghton, right?
哎，
Houghton, right?
是。
是. Okay. Good. Yeah. Okay.
Can you see my screen?
Yes.
Hello. My topic on Lab B is RTL stream kernel integration. This is outline. Because on Monday we already see several good presentations, so I try to cover other thing that I think is important. First, we will see an overview about this tutorial, and I will highlight something that might be useful, or I try to understand something and share my opinion. If I misunderstood something, feel free to correct me. Okay, so in this tutorial, it has 3 kernels, and these 3 kernels, they work together to generate an image. The image consists of time image and a background image. So this is a real-time image mixing, or you can say rendering. And so when you run this,
Wait, Houghton, did you turn the slide? Do you change pages?
no.
So it's still the first page, right?
我重新来一次，我重新分享一次。
Okay.
等一下啊。我直接分享整个画面试试看。
Oh. Okay.
So
yeah, right.
This is outline.
Right. Okay.
So we will first see an overview about this tutorial, and I will highlight something that I think is useful. So in this tutorial, it consists of a host program and 3 kernels. These 3 kernels work together to generate an image. This image is shown on the right top side. This image consists of a clock and a background image. So these 3 kernels run kind of real-time rendering of this image. The first kernel is written in Verilog, and the second and third kernel are synthesized by high-level synthesis. The first kernel called RTCgen, it generates block image. And the second and render 2 image together. The third put the resultant image back to the global memory. So these 3 kernels, they connect by AXI string, as the black arrow shown here. And the kernel communicate with memory by AXI light. So this page shows host and device relation. We will run the host application on our x86 x86 CPU and through a PCI interface, and this HBM stand for the global memory shown here in the blue rectangle, and the 3 kernel are compiled into a single program. So OpenCL is for heterogeneous operation. OpenCV is for image processing. I select some important part of the code because the code is very long. So to run this application, we first initialize. Here we have 3 command queue. I think the reason we need 3 command queue is because each job in a queue, they work sequentially. So in order to run these 3 blocks concurrently, we need 3 queue. And next, we will see more detail about how it works later. And next, we will initialize a program. This bins parameter here is a XCL bin file, which combines several object files that generated by synthesis result. So here we create a program object target to the context. The context is the device. The device, for example, in our server is U50 card. So now we have a program. So for this program, we need a handle of these 3 kernel, function. So we declare the kernel object for each of them. Here we can see the naming convention is specified the module name RTC_gen, and here is Instancenan. Later we will see where we can find a Instancenan. This is just a example about how to read the datasheet. The datasheet of OpenCL looks like this. It defines each function. For example, in the CL namespace, the class program, it has a member function, look like this, and it accepts the first parameter, specify which information you want to get. The second is the return type, because there could be various return type, so it uses template method. Here we see, for example, string class. Because we use template type, in fact, OpenCL allows you to pass not only the C++ standard string, but also you can write your own string class that is compatible with standard string class. Okay, now, so we have initialized program and kernel. Now we allocate buffer. The buffer is because in kernel we need address, we need a pointer information such that kernel can know where the data it need store. So we allocate 3 buffer for these 3 kernel, and we can see a typical allocation buffer allocation looks like this. Oh, by the way, the memory used here is located in the host memory. So we passed the host memory. We took a host memory space as a buffer, and we can specify, for example, use host pointer and read only. On the other hand, we could have write only here. So the buffer is used to transpose, for example, font library. Font library looks like this, a sequence of image of numbers, and the background image, for example, in here we see a card, and output image also need a buffer. So I remember on Monday, we already see how to pass argument from host program to kernel. We use set arg. There is some slight difference between Verilog kernel and HLS kernel. In HLS kernel, we can directly see the argument order from the CPP code. For the Verilog kernel, we need to see some information generated by Vivado. For example, you can find the variable order in this file called, for example, for RTC_gen, we can see corresponding file. It's corresponding XML file here, because if you directly read its Verilog code, you will see a lot of extra signal, such that it is difficult for us to understand what is the actual port we should work with. So my suggestion is to find the synthesis file generated by Vivado, such as this XML file. Now, so we have complete our configuration, right? Now this block shows the main part of execution. For example, we declare 3 command queue, right? For each command queue, we enqueue a task. A task is those kernel we declare. So here we know that a task is something like we ask a kernel to work one time, and we wait then to finish here. So because they are communicated by string, so I think they automatically synchronized by the string communication. So we can directly enqueue our task in maybe different order, and they will work concurrently because they are synchronized by string interface. And now here it use enqueue migrate main object to move the result back to the host memory and wait this job finish. And here it use busy waiting. In this while loop, the condition is always 1. So this is a busy waiting. Busy waiting what? When time change, it will ask, it will update the image. And imagine that if the clock time is not changed, it will stay in this while loop. So the kernel can be idle. So this is kind of busy waiting here. Okay, its execution looks like this. You can change your own background image. Okay, another thing to mention is that information for test bench and host program. Where to find the Instancenan in a XCL program, because the get info only shows kernel name. There's no instance name. The result, the answer is you can find the instance name in this file called XCL bin info, and here is the top label application name. So you can find you can know how to what you should fill in the instance name here to initialize a kernel handle. Okay, and one more thing I want to mention, because I'm not sure, is that on the right hand side we see a XCL bin inform file. On the right hand side we see this file. This file has already been mentioned in maybe lab 1 or lab 2. It's hw.h file. It specifies the register map. And on the left hand side we see, okay, first we see this green block. This green block green block is about argument BGR image input, and its register offset is x10, right? We can find a corresponding offset on the right-hand side green block. But however, when we try to find, we have two string interface here. The first is time image input. It belongs to the port time image input. We can find the port here, time image input. On the other hand, our output is also string. This output called mix image output. It belongs to the port mix image output. So my question is that we see two string. Their register offset is 0, but on the right hand side we see the 0 is some default register preserved for block control. So in my opinion, maybe the string, it has its additional control signal. So its register offset is not shown on the X0 bin inform on the left hand side. So it shows register offset is 0 here. Maybe. Okay, another thing is that the tutorial mentioned mainly the tutorial focused on the kernel level streaming. However, for performance, in order to have good performance, how the function call occur in each kernel, we need to examine how to have a good performance, how to implement those functions within a kernel. So here I highlight 4 things I think that is important, and I try to figure out these 4 things from the tutorial. The first is function argument. This is already covered by the textbook. We can have a HLS string, and we have AP arbitrary precision data type for streaming. And the first is data width. The second to fourth are side channel. Side channel can be found in a reference. Basically, I think because on Monday, Professor Lai mentioned that it is possible to control a kernel by purely data transfer. So I think perhaps we can use side channel to insert some information here. So when a data package sent into a kernel, we can use the information from side channel to dispatch the data to different block. So it's kind of implicitly control of the kernel behavior. The second is local cast. Local cast means that when we have a input string, if our local data is not a string type, then it could become a performance bottleneck. So we need to use pragma HLS string variable to specify which local variable we want to make it a string variable. I search on internet. So if you declare a function argument to be string variable, it will synthesize it as an AP50. For local variable within a function, it will synthesize as a FIFO of depth 1. Okay, next. The third is function interface. Function interface means, okay, within a kernel, we call several functions, right? And this function that if we run Dataflow, then ideally we can run several functions concurrently, but we need to take care their input. So their input need to be string too. And this I show here, these two functions, AXI2 MAT, is a example from Vitis vision library. So it has, because in C++ we have polymorphism, we can have the same function name and different input. So they use polymorphism to adapt to various situations to gain the better performance. Interestingly, for example, in the second type, its input is a string, but its output is a pointer. I look into what happened within this function, because the first type is in and out are both string, but the second is output is just a pointer. So in the second form, it use loop and pipeline to adapt string to pointer. So with the first three bullet 1, 2, 3, in the last, we can unleash the true power of Dataflow. Okay, this is a reference. Thank you.
Okay. Yeah. In this lab that you talk more on the host program for the kernel function. Those three functions, they communicate with the string, right?
Yes. Yes.
Okay. And at the same time, since for example, the alpha mixing, so you accept the string from the RTC gen, and
yes.
also you read the background image.
Yes.
Right, and then you mix them.
Yes.
Okay. So for this part of code, that is there any timing locking, interlocking scheme, or synchronize these two streams and produce the output? Looks like you merge these two and generate one output stream. Yeah. I'm wondering, is there any interlocking or synchronization scheme between this stream, these two
Alpha
streams?
mix. Okay, this is the code of alpha mix. I think. Okay, first, type image input on the line 127 is the type image, and BGR image input on the line 128 is the background image. So
okay.
here we first follow, let me see. Okay, it declare a local variable for type image, and it declared the data of this local storage as a string. But for the background image, I don't think it has background. It also declared background image as a string here on the line 159.
First, you do the the argument for the background image is actually an array or pointer to the memory, right?
Yes.
So you must have a loop to read the memory and turn into the string, internal string, right?
Yes.
And
yes.
then when they mix these two, they need to know what to mix, right? So they must have some kind of synchronization between these two.
I think about because they are string, mixing here.
Oh, mixing is another function. Oh.
Yes. Okay, let's see. Row. The input of mixing. The input of mixing is.
For mixing, the input are all string, right? No, that's a
No.
function. No. Looks like a array.
Yes.
Yeah, both are array.
Yes.
Oh. Okay. And then it use the CV function to mix them. Okay.
Yes, I think so.
Okay.
So maybe here we can have a more detailed optimization about the mix process.
Yeah, and also I think for this lab we can learn how to combine the RTL module and the HLS module into an integrated design. Yeah, and that's the case that that's a quite common, yeah, to see this kind of RTL and HLS mixing. Yeah,
oh yes.
Yeah, it's good to learn from this lab. Okay. Yeah, good. Yeah.
Oh, thank you.
Oh, no more question. Yeah, thank you. Yeah, good.
Hello. Can anyone see my screen?
Yeah, no problem. Good.
Okay. Okay, wait a minute. Okay, the topic I'm going to share is convolution filtering. And here is today's outline. I will quickly overview the whole process and then introduce each lab more detailedly. I will show the results and the performance analysis at the end of each section. Okay, this tutorial goes through the process of analyzing and optimizing a 2D convolution. First, I'm going to introduce acceleration and video convolution filter, and then I will estimate the hardware performance. And then I use VT's HLS to design and analyze the hardware kernel module. The last lab focused on building a hardware kernel using VT's application development flow. Okay. So in lab 0, this lab just compare the performance on CPU and the bitstream file. And this bitstream file is the pre-built hardware optimized accelerator. And since that this pre-built bitstream file is built on U200, so it can be used in the workstation. And this result is the CPU throughput on the workstation. And the throughput is 20 million bytes per second. Okay, let's go in lab 1. In lab 1, I will introduce the video convolution filter and estimate the required acceleration for a given performance constraint, and then I will estimate the performance of hardware accelerator. Okay, video convolution filter has lots of application, and the steps of it is shown here. So we select an input pixel and then extracting a submatrix whose size is the same as the filter here. And we calculate the sum of product of them, and then it is the output pixel's value. And the filter will move, the direction of the filter moves from left to right and from up to down. And the size of frame here is 1920 times 1080. And the size of the filter is 15 squared. Okay, this is some important detail in the source code. First, the convolution filter is implemented using 4-level nesting loop structure. And the inner loop to perform 225 meg operation for each output pixel produced. And then on the boundary of each image, we do 0 padding on it. Okay. So this is the estimation of the performance of hardware accelerator. So without pipeline, the output throughput is only 1.33 million bytes per second, since that for each output pixel produced, it needs 225 cycle, and the maxima frequency in the hardware is 300. So without pipeline, the output throughput is 1.33 million bytes per second. And if we use pipeline, the output pixel will produce for 1 byte. So the output throughput will be 300 million bytes per second. And because there are 3 channels in each image, so the final throughput will be 900 million bytes per second. Okay. And then in this lab, we're going to optimize the hardware implementation and build the kernel using VTC-HLS. The first method to optimize the hardware is using Dataflow process. And this process is, first we read the input pixel from memory, and then we use this function, window 2D, to catch some input value. And this function is relates to data mover, and I will introduce it later. Okay, and it will generate the 15 times 15 input pixel and send it to the function filter 2D. And then it will in this function, it will calculate the sum of products of the submetrics and the filter. And then we'll write the output pixel to the memory. Okay, so this is the source code of it. And here we are going to introduce data mover, which is mentioned in window 2D. And if we do it without data mover, the memory access will meet 451. So it is a large number. And okay, this is the details in window 2D. It works like the size of line buffer is in this example, the image size is 8 squared, and the filter size is 3 squared. So in this example, the line buffer will be 2 times 8. It's the range here. I draw it. Wait a minute. So this is the size of the line buffer. And the window buffer size is the same as the size of the filter. So it is this 3 by 3. Okay, first we see the window buffer. We can see that when the window buffer moves to the another stage, we just have to move this value to here. And this all the value in this column will be abandoned. Okay, and in this column, the value above the value in the first two rows will be put will come from line buffer, and this pixel will come from the memory. So it is the only input in the window buffer. 这边我用中文讲好，我觉得我讲的蛮卡的，就是我们先不要管 line buffer， 我们先看 window buffer。就是 window buffer， 如果我们把这个 pixel 移到这个 pixel 的时候，我们其实只要把右边这2个 column 往左边移1格到这边就好。那新的这个 column 的上面这些值是从 line buffer 来的，因为 line buffer 的高度只有2格，所以它只能给上面这2个值。那最下面这个值就是要从 memory 读进来的这个新的值。好，那接下来 line buffer 是怎么运作？就是跟我刚刚讲的一样，它只有上面这个2×8的大小。那因为其实这个 line buffer 是拿来给 window buffer 值的，所以它其实只要2×8的大小，是因为当我们往右边移1格的时候，其实这个1的值就是已经不会被用到，所以它就会被丢掉。那我们写进来的这个新的值就可以把这个1的值覆盖掉，大概是这样子。对，所以它其实只要2×8个大小这样。好
Yeah. One question about the window. When you move the window, how the internal are they using the shift register?
I can show the source code.
Okay.
It looks like this. And
okay. So yeah. Something like a shift register.
Yes.
Okay.
Okay.
Yeah. Okay.
好，我继续用中文讲好了。所以这边是我刚刚说的那一坨东西，就是当我进来一个新的 window buffer 的时候，它左边这一块来的是左边这一块的资料来源是之前右边的这一坨资料，然后新的这个最右边这个 column 就是从 window buffer line buffer 来的，然后最下面这个值是就是读进来的新的值这样。对，这跟 source code 上面写的差不多。然后line buffer 的话是其实我刚刚讲的这边把1丢掉是错，它应该是把这个4丢掉，就是它前面1、2、3已经被丢掉了。它现在如果照这个 code 讲的话，它是把这个4丢掉，然后把这个新的这个20写进来这样。它其实是把就是每个 row 往上移1格，然后把新的值写进来这样子。OK， 好，然后对，所以这边是 source code， 然后这边是刚刚讲的。好，然后接下来是就是 optimize 的 pragma， 所以因为它这边用到很多 array 跟就是 for loop， 然后它这边会就把那个 array 全部都做 full partition， 然后它会把那个 loop carry 的dependence 都切干净，这样就是让它可以顺利的做 pipeline。然后另外你们看得到我的那个箭头吗？
对。
OK，so 这个 pragma 是拿来做，就是因为它的 input image 有一个上限在，所以如果 input 进来的 image 超过这个大小，它就不能再做下去，它最多只能这个 for 回圈最多只能执行这么多次。然后接下来就是把这个 for 回圈切 pipeline 这样。好，这个是 window 2D 的部分。然后接下来是 filter 2D， 就是这边就是做那个 sub matrix 还有 filter 的 sum of product 的地方。然后所以这边也是会把这个是 coefficient matrix， 就是 filter， 它也会把它做 full partition。然后接下来这边是读进来那个把 filter 读进来的地方，然后它这边也会切 pipeline， 让它一次进来1个。然后这边就是做计算的地方。 然后同样它也会就是切排排，让它就是一个 cycle 只能做一次那个 make operation。OK， 好，然后接下来这边是最后的结果。
Can you go back to the 2D filter?
2D.
Yeah.
Window.
So the 2D, the 2D filter.
Oh, okay.
The 2D filter. So the coefficient only read once.
Yes.
Okay. And then you have the loop. Okay, the full level nested loop is on the right part, right?
Yes.
Okay, there's a full level loop. Okay, the image size X and Y and the window row and column. The filter, yeah, the kernel function, yeah. So it's full level loop, yeah. Okay. Yes, yeah, no problem.
Okay, thank you. And so this is the result of it. 我继续讲中文好了。好
，OK，
这边是最后产生 bitstream file 的地方，然后我会先介绍一下就是 host application 的运作方式，然后接下来是最后的结果这样。好，一开始 host application 就是它会先输进一些 command 的部分，就是像是这边会指定说它用哪一种 filter，就是0到6这样子，然后还有一些指令。然后这边是在读档案，就是把 input pixel 先读进来，然后这边是把那个 bitstream file load 进来，然后还有就是定义一些 OpenCV OpenCL 的东西这样。好，然后它真正在跟 kernel 就是 communicate 的地方是在这个地方，它是用一个叫做 filter 2D dispatcher 的 class。那这个 class 里面其实还有另外一个 class。然后它叫做 filter 2D request。那所以其实在这个 dispatcher 这个 class 里面，它最主要功能就是它会用一个 vector 把要跟 kernel 沟通的 request 先存起来，然后下面再叫这个 filter 2D， 就是刚刚的那个 filter 2D， 这边是会在 kernel 上面算的唯一的function这样。然后这个 filter 2D 会被写在这个filter 2D request 的 class 里面。好，那我们来看一下 filter 2D 这个 request 这个 class 在干嘛？就是这边是就是定义一些等一下哦，这边是定义一些就是 OpenCL 的 buffer， 然后还有就是要传进去的 argument， 就跟刚刚那个同学讲的是一样的东西。然后这边这个 buffer 就是这个是那个 filter 嘛，然后这个是要 input 的 pixel， 就是那个 sub matrix， 然后这边这个就是要读出来的 value 这样。好，然后接下来这个就是 filter 2D 在做filter 2D 那个 function 里面的内容。那左边是就是它是这样子两张这样。好，然后这边也是把一些那个值先传进去，然后最主要做运算是在这个地方，这边会先把这个 filter， 然后还有 input pixel 先写进这个 buffer 里面，要给对，然后接下来这边是那个 enqueue task， 就是等它算这样，然后最后这边是把它的值读出来。对，所以直接这样看 source code 的话，就是大概是这个样子。OK， 好，然后对，剩下这边就是一些结果的部分，然后这边是它处理完图片的样子。然后这边这个问题好像上次有人提到，就是因为那个 AAHLS U50 里面是没有 DDR 的，所以那个设定的时候要稍微改一下，不然会跑不过这样。好，然后这边就是最后加速的结果大概是 40.15 倍，那跟刚刚算的那个 44.6 倍是就是差不多，大概差 10% 这样。OK， 然后对，差不多就是这样子。
等会你这个this speed up that before you didn't count into the I/O time, right? When you do the estimation.
Yes.
You didn't come into the I/O, but this result, the FPGA speed up, including the I/O, right?
Yeah. And since that the estimation results use the maxima frequency. So I think the hardware don't.
It's the only kernel.
Yeah.
Right? Yeah. So for the whole calculation here, it doesn't include the buffer transfer to the kernel, right?
Yes.
Yeah, it's purely for the kernel functions throughput. Yeah, and the actual system running that include the I/O, transfer the source image and the coefficient kernel, right? This time, the FPGA, right?
Yes.
So that can explain why the speed, the improvement is a little bit lower.
Oh yeah.
Okay.
Okay.
Yeah. So yeah, this lab basically we can learn from this lab two things. One is the before you actually implement something, you want to have a good estimation about the expected speed up. It's quite important. Yeah. Okay, and that's a good discipline. Always estimate the target speed up. Yeah. And after the result, you can compare against it. If there's a big variation, deviate from the original estimation, then you should look into the issues. Okay. Yeah. If you don't have a estimation from the beginning, that you cannot judge whether the result is trustworthy, or if there's anything wrong, that you cannot judge. Yeah, so that's a good discipline we should have. And the second thing, I think this lab teaches a very good data structure, the line buffer and the window functions. Yeah, and those are the kernel, the core of many of the video or image processing algorithms. Yeah. So also 新宇嘛，新书。
新宇。
Yeah, Xinyu give a very good explanation on the function for the line buffer and window function. Yeah, very clear explanation. Yeah. Okay, good.
Thank you.
Yeah.
Okay.
Thank
you.
Yeah.
喂，有声音吗？
OK， 好，走哈。
好。OK， 等一下。等一下哦。
Yeah。
过来了。好。这样。Okay. Hello everyone, and today I want to share the topic which is AAHLS, and this is my outline. And in the beginning, I will...
hold on. Since there's some background noise, I don't know where it's from.
Oh.
From your side or?
Yeah.
Oh, fine. Where are you?
Lab.
In the lab. Oh, okay.
Yeah.
No wonder. So it's a very busy lab. Oh, people are still working.
Yes.
Okay. Yeah.
I see. So this is my outline, and in the beginning, I will give you a brief introduction of this is AAHLS, and then I will teach how to create a British AAHLS project in the simulation synthesis and analyze the results, and then we will try some optimization techniques. And finally, I will teach how to explore a VT's kernel to RTL code. Yes. Okay, so VT's high synthesis is a key part of the VT's application acceleration development flow, and it can compile C or C++ and OpenCV code into a kernel for acceleration. Therefore, it is a tool that compiles the hardware kernel for VT tool by performing high-level synthesis. Yes. Okay, so what will we learn in this lab? And the first is create VT's AAHLS project and run the synthesis simulation and analyze the result report and using some optimization on our code and explore the VT's kernel. Okay. And so how to create VT's AAHLS project? And I think it's very similar to the previous of our homework. And so the first is to launch the VT's AAHLS in GUI mode and select create project. Yes, and enter your project name. And you need to choose your source file. And if you have lots of source file, you need to specify which one is the top function. Yeah. Okay, so after include our source file, and then we need to include the test bench. Okay, so in this example, we include the DCT test.cpp file. And this is a test bench for the design that iterate through the kernel multiple times. And we need also to prepare input data and output codon for our test bench. And finally, we need to specify the solution name and specify the clock period we want, and the default is 10 nanoseconds. And then we need to select our box, and yes, and we can choose we want to Vivado IP flow or VT's kernel flow. And in this step, we choose VT's kernel flow. Okay, so now we finish create the VT's AAHLS project. And in this level, we will use 2D discrete cosine transform as an example. So here's the code hierarchy. In the main function DCT, we have three functions: read data, and the DCT 2D, and the write data. And the DCT 2D, it all DCT 1D 2 times, and the first time is for the row operation, and the second is for calculate the current data. Yes. Okay, so how to run the simulation in this tool? We can choose projects and click the run simulation. Okay, and in this tool we can also see the synthesis flow viewer, and this viewer shows the flow path in your C or C++ code, and this viewer allows you to see where the memory rewrites are in control flow graph. And this also allows you to get a sense for memory port contention issue. Yes, and you will see some numbers on the graph. For example, here, this means this is a if-else branch, and this tool will ask which branch the possibility in your or for example, you will go to the right left 88%, and you will go to another row 20%. Yes, it will give you the some information. Yeah, the branch you go into, the possibility you go into which branch. Yes. Okay. So after the scene simulation, we do the synthesis. So the flow is very similar to the scene simulation. We have a scene synthesis button we can click, and here are some steps the VTs actually do scene synthesis flow. Yes. Okay. So the document says that the VTs actually will automatically inline more functions and dissolving the logic in higher level calling function and pipeline small loops with limit iteration. Yes. So for example, after we finish our synthesis, you will see some it will tell you which loops you do the pipeline, and the pipeline results are listed here in the guidance box. Yes. Okay. So this is also give a synthesis result report after you finish the synthesis, and this report is very similar to the Vivado AAHLS we used before. We can see the latency, the iteration latency, the interval, the tree count, and the pipeline. Yeah, and the resource we use. Okay, so let's move on to the optimization techniques. And the first I want to introduce is configure the pipeline loop threshold. Okay, and so this means I mentioned this will automatically do the pipeline in your loops, and you can specify okay, maybe we can say that if we set the number, if the number here is 60, it means the VTS tool will pipeline the loop which iterate number is smaller than 64. So you can specify the number. If I specify 10, and the VTS tool will only pipeline the loops which iteration is smaller than 10. Yes. Okay. And the second one, optimization technique, is configure the pipeline initialization intervals. And we can tell the tools that a specific number of clock cycles before processing another sample is acceptable. And this may possible animate the IA evaluation because the latency will then be match our spec. So how to do this? And choose which function we want to configure. For example, I choose DCT2D, and we can in iterative editor box, and we select pipeline, and we specify the II we want. Yes. And here's the report. We can see the DCT2 its interval become 4. Yes. Okay. The third one is to assign dual pole range with spine storage. And sometimes a guidance message will show unable to schedule no operation, and it indicates the load more of read complete issues with memory transcation. So we can so the specific problem of reading or writing memory possibly be addressed by increasing the available memory ports or read from or write to. Okay, so in VTs, we can specify the type of memory we want to use, for example, 5-port or RAM 2 ports, or ROM 1 port, or ROM 2 ports. You can also choose the source you want to implement this memory. For example, you want to use block RAM or the LAS or the URAM. You can specify in here. Yeah. And fourth is assign and repartitions. Yes, and this is another approach to solve memory port conflicts. An array partition lets us participate an array into smaller arrays or into individual registers of one large array. This is basically either increase the amount of read or write for the storage and potentially improve the throughput of the design. Okay, but however, the array partition requires more memory instances or registers, so it increases the area or resource utilization. Yes. And so how to do this in AAHLS? Okay, so we also can do this in directive editors. So we choose array partition. Yes. And you can specify the filter and the type. Yeah. And the final, I want to introduce Dataflow optimization. The Dataflow optimization tries to create text level parallelism between various functions in the code on the top of the loop level parallelism where possible. Okay, so the top function in our example is DCT. So we choose DCT, and in directive field we choose Dataflow. Yeah, it's very simple. Yeah, so here's the result. We can see that the solution one is the basic design, and after Dataflow optimization, our interval our interval is 65% of the baseline. Yes. Okay, now let's introduce code simulation. Okay, so we can in the solution menu, and we just click CRT code simulation. Yes, and we can choose channel profiling. Yes. We will introduce this later. Yeah. Okay, so So after the configuration completes, the tool will open the report and which will tell us if the configuration passed or not. Yes. Okay. So after the co-simulation finish, we can see the data flow graph. Yes, and the data flow graph shows the overall topology of the data flow. Yes, and the co-simulation data helps with the file sizing problem by tracking the maximum size of the file during the course of the simulation, and thereby giving the user a good reference point to how to size our file. Okay. And now, after we finish the simulation, the synthesis, and the co-simulation, and finally we export the VTIS kernel. So from the main menu, select solutions and click export RTL. Yeah. So you just need to notice where you want to save your file, and you click the OK. Yes. So yeah. Okay. Okay. So the summary is we work with optimized C or C++ code in this tool, and to synthesize it into RTL code for the VTIS application acceleration development flows. And with this code optimized, we export the compiled kernel object file for use in VTIS application project. And these are the elements of building and accelerating application and function using in VTIS and VTIS HLS tool. Yes. So hope you guys know how to use VTIS HLS tool. Yes. So here's my end of my report. Thanks for your listening.
Okay, yeah, I think this lab goes through the whole VTIS development flow. Yeah.
Yes.
Okay, good. Yes.
Okay.
Yeah. Okay, good. Okay, let's move on to next.
Can you see the slide?
Yes.
Okay. And here today I will to talk about the lab B, and the topic is introduction to VTIS hardware acceleration. And this is the team lab, and my name is Lin Yousheng, and my teammate is Ke Zhongxian.
Okay.
And so the first, the introduction, and in this tutorial, its goal is to provide us an easy to follow and its guide to introduction the accelerating application, and it's a simple way to let us to get started with VTIS and how to initialize the function. And in the first, we need to build the hardware design, and it's the node we have to change the platform, and finally we can get this file, and this file contains all of the kernel we needed. And in this step we have 8 examples, and each example will do the design flow we do in the lab 3. So in this in this Mac, it will take lots of time. And in the software design, we can just run this command and it will get the correct test data. And we look in example 0 and loading an image. And this is a very simple example, and it just shows us how to initialize the OpenCV and create the command queue and configure the FPGA. And it have to mention is list header files, and this header file is the library and contain the silence helper function and wrap some of the required initialization function. This is the workflow and how show us how to initialize the OpenCV and load to FPGA. So the first in this code is discover and number the silence device. Yeah, and in here we will initialize the OpenCV context and command queue. And the third, we have to load the binary file target our board. Yeah, this binary file. And the last step, we program the FPGA using the binary file. And the example one is a simple memory allocation. And in this sample, we will run this code. As we can see, this code has not been optimized to run in FPGA, and so it is particular non-efficiency. And if in this code, we can see it will run in CPU more faster than FPGA because the CPU's clock is higher than FPGA. And in this code, is one cycle we do one add. So in order to run something function on FPGA, we need to do the four things. And the first one is allocate and populate the buffer, and we can send and receive data from the FPGA. And the second, we have to transfer lost buffer to host memory to FPGA global memory. And the third is run the kernel. And the final, we have to transfer the result back to host memory space. As we can see, only one of those things actually take place on FPGA. So the memory management will take the very important role when we using the application. So this is the workflows in example 1. And here we can see it's just a simple allocate buffer in normal weight. And it is most important is non-aligned in this allocate weight. And then we can map our user allocate buffer as an OpenCV buffer and use this flag, and it will be a host pointer. And then we need to include and migration the input buffer to global FPGA global buffer. Here, input buffer, yeah. And we can run the kernel, and finally we can read the result of the kernel back to CPU host memory. And we run the example 1, and then it will get some warning message. It is online host pointer, and this will lead to extra memory copy. And in next example, I will explain why this will happen. And this is, we can see in just a baseline runtime, and we can see here FPGA is slower than CPU in here. And in this tutorial, we go to beat the CPU. Yeah.
Yeah. Hold on. I have a question. Which step this warning message show up? It's running in the hardware emulation or hardware?
Hardware, yeah.
Or actually running the hardware.
Yeah.
So the XRT will detect the buffer alignment.
Yeah. In this step,
okay.
It will create all the hardware file.
Okay.
Yeah.
So they actually find out you allocate 4 buffers, right? And
yeah, 4 buffer.
How many buffer on a line? They detect 3. No, yeah, 3 buffers because the address is different.
Actually, in this step, it only 3 buffer have to use, but it use the 4 buffer because it can calculate and add this some runtime. Yeah, in the tutorial.
Okay.
So in example 2, in this example we allocate the memory in simple. So the DMA engine requires the buffer be aligned to 4K bytes. So in this step we will allocate memory in a line. So if the buffer are not aligned, and if we don't explicitly ask for it, and it will be allocated and non-aligned buffer, so we need to use some special flag to allocate an aligned buffer. And what happens if you don't align the buffer is, if you don't align the buffer in the runtime, then they will copy the buffer's content because the content is aligned. It will not copy the pointer, and it will copy the content. So in here, so it say this lead to extra memory copy. It's because about this. So in here, actually, it have many ways we can allocate aligned buffer, and this just one of. Yeah, and we can see here is a 4 buffer. Actually, we just use A, B, C, and D is not used in the code. So in this way, we can change our buffer all into aligned way, and we can see the result. And we only change 4 lines, just change the list and let it be the aligned buffer, and it can improve 100 milliseconds. In here we can see, but now it's still slower than CPU. And example 3, memory allocation with OpenCV. And actually this is just another way we allocate in a line buffer used with the OpenCV. Yeah. So in here we can see allocate our new buffer using this flag. Yeah, it's a new buffer. And the example 2 is the existing buffer, and we pass the pointer to OpenCV. But in here is OpenCV create a new buffer itself. So we no longer need to pass a pointer to OpenCV. So here we need to map our input buffer to this buffer, just A to this one. Yeah, and then we can map our output buffer to migrate them back to host memory. Yes, if you use the OpenCV to create the memory, you can do that. And then finally, we have to unmap the buffer before OpenCV end. Before the OpenCV end, yes, it need to unmap the buffer. You map here, yeah. And we can see it's rather than speed up any particular operation, and it seems like it shifts the latency in the system. And we can see here in the example 2, the buffer population is take more times. And but in example 3 with OpenCL is in buffer allocation is take more time. And you can see here it just shift the latency. It's not pretty improve the runtime in here. It's just another way we can allocate the memory line.
Wait. Yeah, go back. Yeah. So the buffer mapping example 2 and example 3 differ a lot. Reduce a lot. So do you know what the buffer mapping does?
Buffer mapping.
Yeah. Look at that. That's a big difference. Big improvement.
Yeah. I think
buffer
because
population.
example 2 is you have to transfer the user space pointer to OpenCL, and in example 3 is OpenCL create the buffer itself, so you don't have to map in the buffer.
Oh, okay. So I mean example 2 goes to the kernel. Memory allocation is done by the OS kernel.
Yeah.
And example 3 is done in the OpenCL and run in the user space. That's what you mean? Okay.
Example 2 is we create the buffer in user space, but it transfer the pointer to OpenCL. And
yeah. Okay, and here I would like to mention something that when you want to allocate buffer, normally you trap into the OS kernel because OS kernel handle all the memory management.
Yeah.
Okay, and the buffer created in the kernel address space is in the kernel address space, and the user program run in the user address space. So it involves the address translation. Okay. And that's one thing. Another thing is the OS does the memory management, and it doesn't guarantee the buffer address will be by alignment. I think the new OS kernel will at least is a 4 by double wall alignment, and even the new OS kernel, since the memory getting cheaper and cheaper and larger, so that for the efficiency consideration, they may using the 4K alignments. Yeah, but like Intel, there is a DPDK. They actually design its own memory management. So for initially that you will add big chunk of memory from the OS, and later on for all the user address space application, it calls the memory allocation from the DPDK package, and those memory buffer are allocated in user address spaces, and also it makes sure all the buffer allocate is 4K alignment. Yeah. So I believe probably in this example, using a memory allocator which runs in the user address space. Okay, that's one thing. Another thing is remember that for data transfer you use the DMA engine from the FPGA, and for those for the DMA engine in the FPGA, it's a very simple DMA engine. It does not handle all the bio-alignment issues. Okay, so that then the application program has to make sure all the buffer allocate is 4K alignment. Okay, so the good thing is all the communication with the host, with the FPGA, you go through the XRT kernel. Okay, so for the XRT kernel, it will ensure all the buffer allocated. The buffer actually communicate with the FPGA is 4K alignment. So it will check if the user application program does not allocate the memory at the 4K alignment, it will trap and do the memory copy to another memory and make sure that memory buffer is 4K alignment. And then it transfer the data to the FPGA using the FPGA DMA. Yeah. So in order to avoid the double buffering or to eliminate the buffer copy, that it's better that you allocate the buffer 4K align in the address space to start with. Yeah. I don't know whether I explained clearly. Yeah. Okay. Yeah. Let's proceed.
Okay. And the example 4 is parallelizing the data path. Until now, our accelerator have been followed basic same algorithm we have mentioned above. It just perform one 32-bit addition on each clock tick, but our DDR controller naively have a 512-bit with interface. So if we maximize the parallelism, and we can be able to process 6 array elements per clock tick instead of 1. And this is the navy vector accumulate. It's just one DRAM bank and one output bank. And this is the Y vector accumulator. But this is just a simple case, so it just have 2 DRAM bank. But in other case, you can maybe you can use more DRAM bank. So in this way, we can let the data input more big bandwidth, so it can parallelize in the data path. And we can use this flag. Yes, this flag. And this flag can specify the memory bank we need to use for a particular buffer. For example, is this buffer A and is assigned to bank 1, and buffer B is assigned to bank 2. And this is just change about this data path, and we have managed to beat the CPU. We can see here, and this is a very mass improvement. Yeah, and this is just a simple case. And but if your function is more complicated, and you can parallelize the data path, and it maybe can achieve more higher performance. You can improve. Yeah. And the example 5 will be my teammate.
And can you see my slide?
Yeah, okay. Yeah, no problem.
Okay. And in example 5, we want to do the pipeline kernel execution. And we do the pipeline by we will subdivide the buffer before tuning up transfers. And by subdividing the buffer in this way and choose a optimal number of subdivision, we can balance the execution and the transfer time for our application and get significant higher throughput. And then we can create the subbuffer by using the create subbuffer. And then we can choose the region and then choose the area. And the loop will be like this, and it will split to any part. And we can see in the time compared to example 4. Then we can find that in the software part, the time may be large, but in the hardware part, the time we use will less more. This may be because the PCIe bandwidth is much lower than the card we use. Then the benefits are great when we perform pipeline precision. Because when we do pipeline, then the data we send into the card one time will not many much, so we can do the hardware part more faster. And in example 6 is BADD with OpenMP, and in this part we use another algorithm to do parallelize. And in this part we use the pragma OMP parallel 4 to do the parallelize. And why we use the different algorithm? Because for simple algorithm, the accelerator just won't win the CPU. So we want to try another algorithm. And we can find that in example 6, the last line of the time, we can find that in our card, we do faster than the CPU. And this is because we use a new algorithm in OpenMP. So we can get the result. And in example 7, we want to do the resize and use the OpenCV image resize. And in this part, we want to do the bilateral resize algorithm. And the step is, first we read the pixels of the image from memory. And then, if necessary, we will convert them to the proper format. And for the color image, we will extract each channel, and the channel is RGB, and use a bilateral resizing algorithm on each independent channel. And then we will recombine the channels and store back in memory. And this is the step I talked about. Just first read the data, and then we extract each independent channels, and then we do the resize in each channel, and then we recombine the data. Then we can get a resize data. And because of the way we configure the hardware in this example, so the image must conform to certain requirements. And in this example, the input width must be a multiple of 8 because we're processing 8 pixels per clock. And this is the example we did. And in the scale down, we reduce the height and width 3 times. And in scale up, we times 3 and in the height and the width. And we can see that when we do the scale up, the time we need is more. And in example 8, we do the OpenCV image resize and blur. And the difference from example 7 is a Gaussian filter is added after bilateral resize and before recombination. And the Gaussian filter is a very common pipeline stage to remove noise in an image before an operation, such as edge detection or corner detection. And then we use the Gaussian filter by CV Gaussian blur. And we can set the size we want to do and just the kernel size. And we can set the standard deviation to 3 or to another data. And in the example, the input 1 must be a multiple of 8 because we are processing 8 pixels per clock. And we can see that in the scale up, we compare the time of example 7, and we can find in example 8, we add a Gaussian filter between bilateral resize and recombination. So we need more time to do example 8. And this is for our presentation. Thanks for listening.
Hello, may I ask a question?
Okay.
Are you sure it's bilateral? Because according to my memory, there was something called bilinear interpolation in the Vitis Vision Library. Are you sure it's bilateral or bilinear?
I checked the code in example 7, and I can find it use the bilateral filter, but it just used the CV resize to do the resize. So I'm not sure it's used the bilateral resize or just another resize algorithm.
Oh, I see. Oh, okay. Thank you for the response. Now I see what happened there.
Yeah.
Okay.
So just use the CV library. Oh,
yeah, just
video.
use the CV library.
Right. Okay. Yeah. Okay. So for the you say it does the parallel processing, handle 8 pixels at a time. What's the data type it use? Does it use a vector data type?
Oh yes, use the vector data.
Oh,
yeah.
Okay, yeah. And the vector data type, the number of elements is defined as a macro, right? So you can easily change different parallelism.
Yes.
Okay. Yeah. Can you show the code that does it? Okay. My question is when you use a vector data type to do the SIMD like parallelism, do you actually use a row factor equal 8, for example, or it doesn't use a row? It will look at the data type. It's a vector data type. In that case, that you don't actually need to use the enroll. It will automatically enroll for the Oh, you need to look at the kernel. Is this the kernel? In Q. No, that's a host program, right?
Oh,
this
yes.
Is, you need to look at the kernel code.
I don't have the kernel code because we do that in Yosense was stationary. So.
Oh.
Yeah.
Oh, it's only the host code.
Yeah, the host code is in the GitHub.
Only the host code, no kernel code in the GitHub.
Yeah. The kernel code it will build automatically in the first step. Yeah.
Oh.
Yeah.
Yes.
So in this tutorial, we just can run the example and look how it happened.
Oh. So the open source doesn't include the kernel code. Okay. Yeah. Okay, that's fine. I'm just curious. So the data type, if it's vector data type, the AAHLS should do the enroll automatically. That you don't actually need to specify the pragma enroll. Yeah. Okay. Yeah. That's fine. Good. Then let's proceed.
So can everyone see my screen?
Yes.
Okay, so my topic is host site optimization. This is the outline. So first I will briefly introduce this tutorial and then introduce the design of the kernel and the host. And then 3 optimization methods are introduced. And finally, is a brief conclusion. So in this tutorial, 3 methods for host site optimization are given. There are first one is pipeline kernel execution using out of order event queue, and the second is kernel and host code synchronization, and the third one is OpenCV API buffer size. And during the tutorial, only the host code is modified, and we will keep the kernel the same, and to see the modification on the host code, how the modification will affect the performance. So here we first see the design of the kernel. So this kernel is only for the demonstration purpose, and we can see that the kernel basically do 3 things: read, execute, and write. And for read and write, they use a stream interface and prepare the data. Also, the 3 steps are using Dataflow to execute. And for this function, it will consume some input, and the number of input is specified by num inputs. And for each input, it will delay specified by process delay. So this is basically what the kernel is doing. And in the host code, it will call the kernel several times, as shown here. So basically for the run function, it will do the following things. You will first write data.
Can you hold? Can you go back 1 slide, the previous slide? Okay, look at the code here. Yeah, especially the process delay. Yeah. So for this code, actually, it will delay process delay number of cycles, right?
Yes.
Using the for loop.
Yes.
Yeah. So that's an important thing. Yeah. So in your design, how do you add the delay? Number of cycles, you just use a for loop with the process delay. Yeah. Okay. So yeah, sometimes people don't know, how do I design a kernel to intentionally delay number of cycles? Yeah. So that's the way how you can do it. Okay. Yes. Yeah. Please proceed.
Okay. So the run function will first write data to the accelerator and then set up the kernel and run the accelerator, and finally read the data back to the FPGA. Read the data back. And the run, for the run function, we can also pass in an event that it should depends on, which will be used later. So here is the first optimization method, which is we want to enable out of order event queue. So we pass this flag when calling CL create command queue, so that we can enable out of order event queue. So here shows the timeline before and after we enable out of order event queue. So here, write and kernel and read is a task. So we can see that if we disable out of order event queue, then each task can only be executed after the previous task is finished. So they are executed sequentially, one after one. On the other hand, if we use out of order event queue, then each task can be executed concurrently. So here is a task, and in fact, this one is another task. So we can improve the performance. And then is the second optimization. It is kernel and host code synchronization. So in the original host code, we only synchronize once after all the tasks are finished. There may be some problem by when doing so. The first is that we can only release the buffer after we guarantee the task is finished, so that the buffer is not needed. So we may face a problem that we may run out of memory. The second is the order of executing different invocation may differ from the in-queue order. So the host code may wait for a task for a long time, which effectively disable host code parallelism. So to solve this problem, two methods are introduced. The first is that we can insert more CL finish. And the second is we can use event wait list. So for the first method, here shows an example. So for every 3 tasks, we call CL finish again once. So the timeline is shown in the lower figure. We can see that we so for 3 tasks, there will be a CL finish. So we can see that for each CL finish, we can release the buffer previous used, and we can see that no overlap is allowed at synchronization point, and there is a big gap between each CL finish. And this is the second method that use event wait. So here it shows that for task I, it will be run after task I-3 is finished. This is done by pass the done event of task I-3 into the event wait list of task I. So here is the timeline. First, we can see that we note that since task I is executed when task I minus 3 is finished, so buffer can be released. Second is that we can see the red box here. It indicates that the fourth task is start, and it is after the first task is finished, as shown here, and it is before the second task is finished, since the second task is finished here. So we can see that by doing so, the overlapping is allowed.
似懂非懂啊，懂一半而已，根本就。
And this is the third optimization, which is OpenCV API buffer size. So basically, this is done by modify the buffer size. It is an argument when calling CL create buffer. And this figure shows the experiments done by we run on the FPGA card using different buffer size. And so the plot shows the throughput and buffer size. We can see that larger buffer size can lead to higher throughput, but it will saturate at the end. So this is a conclusion. So 3 host optimization are introduced. So first is to use out of order event queue. So we can execute different tasks at the same time. The second is about synchronization. So to prevent run out of memory. And finally is about buffer size. We can use a bigger buffer size to improve the throughput. So this is the end. Thank you.
Yeah, let's go back to the second optimization method. Using the so I think we can all understand that try to avoid using the CL finish, because the CL finish you will wait all the previous task finish before proceed. And then in this example, we use the wait event of the let's say here. The task, it will wait for task I minus 3. So that means you suppose you have 3 buffers. And then after 3 tasks, then you can free up 1 buffer. And then you can have the fourth task proceed. So the question is right now you half fix the stream. So actually we can adjust how many outstanding transactions. For example, in this example, you have 3 buffer available, so you can only outstanding 3 tasks. So the fourth task can start only when the first task finish. So this that's very much like the total latency, including all the data transfer and the execution of the task. Then we decide number of outstanding transactions we want to support in order to fully optimize the I/O bus bandwidth. Remember, in the class we discussed about the XI master first, and the number of outstanding read requests. The number of outstanding requests depends on the latency. So in order to maximize the data bus, you want to put more outstanding transactions. But the more outstanding transactions consume resource. In this case, you consume the data buffer. So we use these techniques to number three here, that's the design criteria. Yeah, you need to find out the right number of outstanding transactions. Yeah, in order to the minimum number of outstanding transactions in order to maximize the I/O bus. Yeah, that's the design target. Yeah. Yeah. So I think that there's a good design technique that we can all learn from it. Yeah. Okay. Yeah, good. Yeah. So yeah. Is this the last presentation today?
I think so.
Yeah,
Okay,
it's the
okay.
last one.
This is the last one. Okay, good. Yeah, so we finished the level B. Yeah. Okay, so if no more questions, that we can finish today. Good. Yeah.